To calculate the linear velocity of an object in motion around a circle, we need to recognize that the distance traversed by that object is an arc of the circle. Understanding that linear velocity is the change in distance divided by time, the length of that arc will determine the linear velocity. Recall previously we labeled the arc S. Here's the definition of linear velocity. If a point is in motion on a circle of radius r through an angle alpha radians in time t, then its linear velocity is given by v equals s over t, where s is the arc length, and remember we have a formula for that, s equals alpha r. So as the object in motion moves across that arc that we've labeled S, the angle that subtends that arc we're calling alpha, and the radius of that circle is r. Let's examine linear velocity in example 4. Find the linear velocity of a point on the tip of a 30-foot windmill blade rotating at 400 revolutions per second. Give your answer in miles per hour and round to the nearest tenth. So we're going to consider a point on the very tip of this windmill blade. As the windmill turns, that point travels around in a circle. If that little point had a speedometer on it and we could observe how fast it's going, that's what we're measuring here for linear velocity. Now, do notice we are given the angular velocity of that point. Omega generally represents angular velocity, so we could make the observation that the angular velocity is 400 revolutions per second. To find the linear velocity, we can simply convert that measurement into miles per hour. So we'll start with the information we have, angular velocity, 400 revolutions per second, and we want to convert revolutions to miles. So let's begin by converting revolutions to feet. In one revolution around this circle, that point will traverse the entire circumference. Recall that the circumference of a circle is given by the formula 2 pi r, and because the windmill blade is 30 feet long, we know the radius of this circle is 30 feet. So the circumference of this circle then is 2 pi times 30. At this point, we have successfully converted revolutions to feet, but we don't need feet, we need miles. So we'll introduce another fraction where we put feet in the denominator and miles in the numerator. Then we'll fill in the appropriate relationship. In 1 mile, there's 5,280 feet. As you can see, our current units are miles per second. We're almost there. We need miles per hour. So let's introduce yet another conversion fraction here where we cancel the seconds by putting them in the opposite place in the fraction, and we put the hours that we need in the denominator. We know in 1 hour there's 3,600 seconds. And at this point we can see, because our seconds cancel here, our units are now miles per hour. Now we can multiply straight across the numerators and straight across the denominators to obtain the value for linear velocity. So we need to multiply 400 times 2 pi, and I'm going to leave off the pi in my calculation. I'm just going to multiply the constants. 400 times 2, leaving off the pi, we have a 30, and also in the numerator we have 3,600. So the product in our numerator is quite large. We have 864 followed by 5 zeros, and then don't forget a pi. We didn't multiply that on the calculator in order to keep this an exact calculation, but we'll evaluate that here in just a minute. In the denominator, we have 5,280, and recall we're looking at units miles per hour. I'm going to go ahead and cancel a factor of 10, and we can do that just by marking out one of the zeros, and then we need to evaluate 8,640,000 pi divided by 528. So we have 8,640,000 times pi divided by 528. This gives us 51,407. We're going to round to the nearest tenth, so 0.9. That is 51,407.9 miles per hour. That is booking it. I'm thinking that for the windmills out here in Texas on the plains, they're enormous. 400 revolutions per second is probably nowhere near the actual angular velocity of those giant windmills. If this were the case and you were a ladybug on the end of that windmill, you would be in for a ride. Now, let's see if we can answer this question. How would our answer for this example change if the windmill blade was even longer? So imagine being a ladybug on the end of a 32-foot blade. You would be traveling around a larger circle, still with the same angular velocity. So you're going a larger distance in the same time. That means that your velocity would have to be faster. So we could make the observation, if the radius increases, the velocity would also increase. Now, for either case, the 30-foot blade or the 32-foot blade, the angular velocity doesn't change. We're still looking at 400 revolutions per second, but the linear velocity changes. So we need to make an important observation about linear velocity, and that is linear velocity, unlike angular velocity, is dependent on the radius. Angular velocity is independent of the radius. Linear velocity is dependent on the radius. Let's try example 5. Find the linear velocity of a point on the tip of a 22-inch lawnmower blade rotating at 2,500 revolutions per minute. Revolutions per minute, also known as RPMs. Give your answer in miles per hour and round to the nearest tenth. Notice in the picture that the measurement given, 22 inches, is a diameter. In order to calculate linear velocity, we need to know the radius. The radius is half of the diameter, so we're looking at an 11-inch radius for this lawnmower blade. The measurement given, 2,500 RPMs, is an angular velocity. So let's make the observation that omega, angular velocity, is 2,500 revolutions per minute. In order to answer the question, we simply need to convert this angular velocity to linear velocity by paying attention to those units. So we're going to start with 2,500 revolutions per minute, and we need to convert revolutions to miles. So in 1 revolution, we're going to put revolutions on the bottom to cancel. In the top, we need to convert this to miles. Now, before we get to miles, because the radius is given in inches, I'm going to convert one revolution into inches. Now, remember, 1 revolution around this circle, the point on the tip of that blade is going to travel or traverse the circumference of that circle. So in 1 revolution, we need to calculate the circumference. That is 2 pi times the radius, 2 pi times 11. Now, if I want to convert revolutions to radians, then in 1 revolution, there's 2 pi radians. But I'm converting 1 revolution into a linear distance, so we need to evaluate circumference formula here, 2 pi r, 2 pi times 11. Observing our units, at this point we have inches per minute. So let's do the work and convert inches to miles. So we're going to do a little stop in the middle here with feet. In 1 foot, there's 12 inches. Then we can convert feet to miles. We know that in 1 mile, there's 5,280 feet. Double checking here, inches cancel, feet cancel. Our current units are miles per minute. We need to convert this to miles per hour. So let's cancel the minutes. We'll put those on the top. and we'll put hours on the bottom, and we know that in 1 hour there's 60 minutes. Our final units then end up being miles per hour, and that was our goal. Now I'm going to multiply everything in the numerator except the pi. I'm going to leave that for the last step. So let's evaluate 2,500 times 2 times 11 times 60. Remember, I'm leaving out the pi. In the numerator, looks like we have a 33 followed by 5 zeros. That's 3,300,000. Don't forget we had a pi there as well, and in the denominator we need to evaluate 12 times 5,280. That gives us 63,360. And our units, remember, are miles per hour. I'm going to go ahead and mark out one factor of 10. Then we simply need to evaluate 33 with 1, 2, 3, 4 zeros times pi divided by 6,336. And we end up with 163 to the nearest tenth. That would be 0.6, 163.6. And that is miles per hour. So if a ladybug is riding on the lawnmower blade, still going for a pretty good ride. Going to leave you with this thought. This is most important to obtain from this section. Linear velocity is dependent on the radius, while angular velocity is not.